Imagine boarding a train in northern Japan, and instead of staring out at mountains or cities, you're surrounded by the deep blue ocean. Every part of this incredible concept is inspired by real engineering principles. Now, before anyone starts packing a suitcase, this tunnel doesn't exist. Yet. It's a futuristic engineering vision built around technologies that engineers already use today, pushed a few decades into the future. And honestly, if humans can land robots on Mars, building something this crazy doesn't sound completely impossible anymore. Japan has spent decades mastering some of the world's toughest infrastructure challenges. Earthquakes, powerful ocean currents, rugged coastlines, and deep-sea construction have forced engineers to think differently. That's exactly why this imagined project belongs here. Our journey begins far before the first piece of glass ever touches the ocean. Every massive construction project starts with one thing that isn't exciting: paperwork. Just kidding. It actually starts with data. And in construction, good data can save billions of dollars and a lot of embarrassing mistakes. Survey ships spread across the cold northern waters between Japan's mainland and a distant island. They don't just look at the surface. Powerful sonar systems map every ridge, trench, and hidden slope beneath the waves. Floating buoys record tides and current speeds day after day, while seabed sensors monitor movement that could affect the future structure. Meanwhile, remotely operated underwater vehicles crawl across the ocean floor like mechanical explorers. Equipped with cameras, lasers, and robotic arms, they inspect rock formations, measure sediment depth, and search for the strongest possible route. Geotechnical drilling rigs extract long cylindrical core samples from beneath the seabed, revealing layer after layer of rock, clay, gravel, and compacted sediment. Every sample tells a story. Can the seabed support thousands of tons of tunnel segments? Will shifting sediments create long-term stability problems? How much pressure will every section experience over decades beneath the ocean? These aren't guesses. They're calculations that determine whether the entire vision stands or never leaves the drawing board. As engineers analyze millions of data points, a digital blueprint slowly comes to life. The tunnel's path is adjusted meter by meter, avoiding unstable ground while following the safest geological corridor beneath the sea. From above, the ocean looks calm and empty. Below the surface, however, an invisible highway is being designed, one calculation at a time. With the tunnel route finally approved, the real construction begins. And this is where the coastline transforms into one of the busiest engineering sites in Japan. Within weeks, the quiet shoreline becomes a city of heavy equipment. Tower cranes rise into the sky, excavators reshape the land, temporary access roads snake across the site as trucks deliver thousands of tons of steel, concrete, and machinery around the clock. Before heading underwater, engineers first construct the land connections. Huge excavation crews dig deep approach tunnels from both the mainland and the island side. These aren't the transparent sections everyone is waiting for. They're the rugged backbone of the entire transportation system. As tunnel boring equipment advances through solid ground, workers immediately reinforce every newly excavated section. Thick reinforced concrete linings are installed layer by layer, followed by dense steel reinforcement cages that strengthen the structure against ground movement. Waterproof membranes wrap the tunnel walls to stop groundwater intrusion, while rock bolts anchor unstable rock formations overhead. Ventilation ducts, drainage channels, emergency walkways, communication lines, fire protection systems, electrical conduits, and maintenance access points are built directly into these concrete passages. While excavation continues underground, something extraordinary is taking shape several miles away inside enormous coastal fabrication facilities. Instead of building the transparent tunnel in the ocean, engineers manufacture every section indoors where quality can be controlled down to the smallest detail. Each module is designed as a giant cylinder, not a square box. There's a very practical reason for that. Ocean pressure pushes equally from every direction. A circular shape spreads those forces evenly across the entire structure, reducing stress concentrations that could develop around sharp corners. It's the same principle used in submarines, deep-sea habitats, and pressure vessels around the world. The structural skeleton begins with precision-machined titanium steel rings. These circular frames are connected by longitudinal titanium ribs, creating an incredibly rigid cylindrical framework capable of supporting enormous external pressure. Next comes one of the most delicate stages. Using giant vacuum lifting systems, crews carefully position massive curved glass panels into each circular frame. Every transparent panel follows the exact curvature of the tunnel, allowing the cylinder to maintain continuous structural strength while offering breathtaking panoramic views of the surrounding ocean. High-performance waterproof polymer gaskets are compressed between every connection, creating the first barrier against seawater. Engineers then inject advanced sealing compounds around every glass-to-metal joint, forming a secondary defense system designed to protect the structure for decades. Piece by piece, the futuristic tunnel begins taking shape, not beneath the sea, but inside a factory where precision matters more than speed. Proving it can survive thousands of tons of ocean pressure? That's where engineers earn their coffee. Before a single module is allowed anywhere near the sea, every transparent cylinder goes through an intense series of structural tests. If even one section fails inspection, it doesn't get a second chance. It goes back for repairs or is completely rebuilt. Each completed module is carefully lowered into a massive curved testing cradle that perfectly supports its cylindrical shape. Hundreds of sensors are attached across the glass panels, titanium ribs, support rings, and connection flanges. Hydraulic equipment begins simulating the crushing pressure these sections will eventually face beneath the ocean. Slowly, the pressure increases. Computers constantly monitor microscopic glass movement, seal compression, flange alignment, and structural deformation. Engineers aren't looking for dramatic failures. They're searching for tiny changes measured in fractions of a millimeter, because small problems underwater can eventually become very expensive problems. Every waterproof gasket is inspected for leaks. Advanced cameras scan every glass-to-metal connection, while ultrasonic testing searches for hidden defects invisible to the human eye. Now the project moves offshore. The calm blue water suddenly becomes a floating construction zone. Massive barges carry the completed tunnel sections toward the installation route. Heavy lift cranes tower above the ocean while survey vessels constantly verify positioning using GPS, sonar, and underwater navigation systems. Far below, remotely operated underwater vehicles, or ROVs, are already waiting on the seabed. Think of them as the construction crew that never needs a coffee break. Crane cables lower the enormous cylinder into the water with incredible precision. As sunlight fades through the deep blue sea, the glowing structure descends toward its permanent home. The ROVs move alongside it, constantly checking orientation and distance. Tiny adjustments are made as hydraulic positioning systems guide the module above its anchor bases. Finally, the support shoes settle perfectly into their locking seats. Hydraulic clamps secure the cylinder to its foundation, and only after engineers confirm every connection do the crane cables release their load. But installing one section is only the beginning. Another module arrives. Its circular end flange is carefully aligned with the first using laser guidance. Heavy-duty waterproof gasket rings are compressed between both sections before powerful locking systems pull the cylinders together into one continuous structure. Every joint is immediately pressure tested, scanned, and electronically verified before work continues. Piece after piece, the glowing tunnel stretches farther across the seabed. From above, ships see only open water. But beneath the waves, an extraordinary corridor is quietly taking shape, one precision-engineered module at a time. The first priority is safety. At both ends of the transparent section, enormous emergency flood doors are installed, where the reinforced concrete tunnels transition into the glass corridor. Next comes the hidden infrastructure that passengers will never notice, but engineers certainly will. Power cables run through dedicated service conduits alongside high-speed communication lines connecting thousands of sensors throughout the tunnel. Leak detection systems continuously monitor pressure changes, while monitoring cameras provide a live view of every critical section. Ventilation equipment, drainage pumps, emergency lighting, fire detection systems, and automated control networks are installed one after another, turning an empty structure into an intelligent transportation corridor. Now, the railway itself begins to appear. Vibration isolation pads are placed along the tunnel floor before precision steel. Rails are installed and laser-aligned over the entire route. Electrical power rails are connected. Signaling equipment is calibrated, and communication systems are synchronized so every component can operate as a single network. But nobody is inviting passengers just yet. The first vehicle to enter the tunnel doesn't carry people, it carries data. A compact autonomous inspection vehicle slowly rolls through the entire route, scanning rail alignment, structural movement, vibration levels, electrical performance, joint stability, and every sensor installed during construction. Every meter is analyzed before engineers approve the next stage. Only then does the first full-size train begin its cautious trial run. It accelerates gradually through the reinforced concrete approach tunnels before entering the transparent underwater section for the very first time. Every system is monitored in real time. Power supply, flood doors, lighting, ventilation, drainage, communication networks, structural behavior, and rail performance. If even one reading falls outside its design limits, testing stops immediately. After countless successful test runs, construction barriers finally disappear. Observation platforms inside specially widened tunnel sections receive crystal-clear safety barriers, while elegant blue lighting washes across the titanium ribs, creating the illusion that the train is floating through the ocean itself. Every glass panel is polished until the surrounding sea becomes breathtakingly clear. Then comes the moment everyone has been waiting for. The first passengers step aboard. As the train glides beneath the ocean, schools of fish drift past the panoramic glass walls, sunlight dances through the water above, and the tunnel transforms from a remarkable engineering achievement into an unforgettable experience. This underwater railway may exist only as a visionary concept today, but every incredible innovation begins with imagination backed by sound engineering. Today's impossible idea can become tomorrow's blueprint, and perhaps one day, somewhere beneath the waves of Japan, a journey like this won't be science fiction anymore.